Okay. Oh, yes. Okay. So I think we can start. Good afternoon. So eventually we go to the last talk of this workshop, and our last speaker is Yasunori Lee from IPMU. He will tell us about matching higher symmetries across Intriligator-Seiberg duality. Please.
Okay, thank you for the introduction, and thank you all for coming. And I would also like to thank the organizers for kindly inviting me to give a talk in this wonderful workshop. So today I'm going to talk about our recent work based on this paper with Kantaro Omori and Yuji Tachikawa. So as the title shows, what we did can be summarized as follows. So we took up certain QFTs in 3+1 dimensions, which possess what we call higher symmetry structures. And we verified that these higher symmetry structures match perfectly across certain supersymmetric duality. So that's what we did. Yes. I don't want to take off the mask, sorry. Sorry. If you don't, do you hear me? Sorry, forgive me. Forgive me. Okay, so first I will explain what these higher symmetries are, and then we'll look into concrete examples with such higher symmetry structures, namely SO gauge theories and spin gauge theories. And these gauge theories are actually related to each other by certain transformations. And exploiting relation, we can indeed see how these higher symmetry structures are mapped under the Intriligator-Seiberg duality. And finally, I will tell you another story about the anomaly, which kind of supplements the argument in the previous sections. So that's the outline of my talk. So let's start by a lightning review of higher symmetry structures. So since we've already heard a lot about it from several speakers from the last week, I'll be very brief here, but anyway. So recall that the modern point of view is that the symmetry can be described in terms of topological operator. So for ordinary symmetry, we have a local operator charged under the symmetry. And the symmetry action can be implemented by a surrounding codimension 1 symmetry operator, which is labeled by the group element G of the symmetry group. So when this, let's see, how should I? Yes. So when this charged operator crosses this codimension 1 symmetry operator, then it gets acted by symmetry. And as a result, it acquires some factor depending on the label G of the symmetry operator, and also on the charge or the representation of the operator itself under the symmetry. So one can immediately generalize this to higher dimensions. So for example, if we have line operator charged on the symmetry, and then this time symmetry operation can be implemented by surrounding codimension 2 operator. So if the line operator crosses this codimension 2 operator, then again, it gets acted by symmetry, acquires certain factor depending on the label of symmetry operator and the charge of the line operator. And in the same way, one can consider the arbitrary generalization, where the charged operator is p-dimensional, and the symmetry operator surrounding it has codimension p+1. And this is what is called p-form symmetry. So in this term, the ordinary symmetry corresponds to p equals 0 case. So it is actually a 0-form symmetry. And similarly, the line operator case corresponds to p equals 1. So it is actually a 1-form symmetry. So far, so good. So next, let's discuss the mixing between the ordinary symmetry and higher form symmetry. So given a QFT, it can, of course, have several kinds of symmetries. And in particular, it can have both 0-form symmetry H and 1-form symmetry gamma. Furthermore, these two symmetries can not just coexist, but also can have mixed tooth anomaly between them, meaning that they might not be able to be gauged at the same time. So for example, we heard from Pietro that in 5D, we have zero form 5D gauge theory, you have zero form U1 instanton symmetry, and also a one form center symmetry, and there was a mixed tooth anomaly between them. Or also we heard from Daniel that in 4D Yang-Mills theory with theta equals pi, there's a zero form time reversal symmetry and one form center symmetry. And there was a mixed tooth anomaly between them, which prohibited the IR theory to be trivially gapped. So this is the simplest type of higher symmetry structure. But there's another interesting mixing of symmetries one can consider. So we know that there's something called group extension. So if you have two groups, H and gamma, you can combine them into a larger group G, which is not necessarily a direct product of H and gamma. So for example, if you take H to be Z2 and gamma to be also Z2, and combine them, so one possible combination is of course Z2 times Z2, but you can also have Z4 as a combination, which is Z2 non-trivially extended by the other Z2. So that's the group extension. But the interesting thing here is that one can play the same game for symmetries with different forms or different P's. So if you have zero form symmetry H and one form symmetry gamma, one can actually combine them by extending H non-trivially by gamma. And the resulting larger group is what is called the two group. So this rather subtle, exotic looking symmetry actually appears in rather familiar theory, as we will see later. But before going on, I would like to make a brief comment. Okay, yes.
So when you write this short exact sequence,
yes,
do you literally mean G as a group in the middle, or it's just intuitive at this level?
On you mean this one, right? Sorry, I'm not doing well, but
in the second line,
the second one, right? It's kind of in how should I say? It's kind of literally this, but it might better be thinking it as some kind of bit intuitive thing, maybe. Okay. There's some formal aspect of it. There's some point which is not totally intuitive in this, but yeah.
Yeah, I'm asking because sometimes in the math literature, they describe two groups with exact sequences, but with 4 elements as opposed to 3.
4 elements, not 3. I think what I
and some equivalence classes among them.
What you are saying. Okay. I see.
Anyway.
Do you know what the structure would be if you would extend a 1 form symmetry group by a 0 form symmetry group?
That I don't know. Sorry. It's that's another question I want.
Or generally like an M form symmetry group by an N form symmetry group?
No, I don't know. Yeah.
Okay.
So for N group, we have 0 form symmetry extended by N form symmetry, but yeah, I don't know the opposite. What happens with when we exchange the
thanks.
Thank you.
So later you will explain how this G acts, okay? Because one acts on point and the other acts on line.
Yes, I will.
Okay, you will explain how this acts. Okay,
yes.
Thank you.
Okay, so yes, before going on to the example, so I want to make a comment. So let's confine ourselves to 3 + 1 dimensions here and take gamma to be a finite abelian group. So then you can actually consider gauging gamma 1 form quote unquote subgroup of this 2 group symmetry. And the gauge theory turns out to have 0 form symmetry H and 1 form symmetry gamma hat, which is the Pontryagin dual of gamma with certain mixed-Tooth anomaly between them. So the two group here is actually controlled by a certain cohomology class. And this cohomology class is in some sense inherited to the mixed-Tooth anomaly on the gauged theory side. So you can also do the opposite. So if you start from theory with mixed-Tooth anomaly between zero-form symmetry H and one-form symmetry gamma hat, and then gauge gamma hat one-form symmetry, then you come back to the original theory with two-group symmetry G. So that's what you can do. And this will be important later, but you can just forget about it for now.
Sorry,
Yes.
simple question. You say that gamma is finite.
Yes, gamma is finite.
Is that relevant for this gauging procedure, or you can consider?
Yes, so for actually, so for non-finite case, I'm not sure this operation, I mean, the opposite concrete form of the opposite operation, inverse operation.
You mean the?
Yes,
the up,
going
arrow,
upside,
okay.
yes. I mean, it's, how should I say? So it's, so one can do this in this way since the representation, how should I say, character group of gamma is, how should I say, easily described in terms of group. So that's why we can do this. I mean, for generic, how should I say, continuous group, you mean, right? Then this ungauging side is, I think in general, it's not this simple. Yes.
Okay.
So that's why we are confining ourselves to gamma finite case. Yes.
Okay, thank you.
So this is in 3+1 dimensions or is general?
Sorry?
This is in 3+1 dimensions?
Yes.
Right. Okay.
Also, 3+1 dimension comes into the fact we have gamma hat one form symmetry on the gauged side. In different dimensions, you get different form gamma hat symmetry. But yes.
If I can add a comment on this, I mean, if you gauge a continuous symmetry,
Yes.
then I guess you're also gonna get some dynamical degrees of freedom. So I mean, the fact that the group at least is discrete means that when you gauge it, you don't introduce degrees of freedom, which I guess is important for this story. It would be more complicated to study the case in which you gauge a continuous symmetry.
Yes. Thank you for the comment. Yes. Okay, so with this, we are now ready to look into great examples with these higher symmetry structures. So let's proceed. So let's start by considering spin gauge theory and see how they are related to SO gauge theories. So first of all, the spin group is a simply connected double cover of the SO group. And here we are interested in spin even case. So we consider spin 2NC group. And the center of the spin 2NC group is known to be either Z2 times Z2 for NC even case or Z4 for NC odd case. So in pure spin 2NC gauge theory, these centers become the one-form symmetry of the theory. So that's the spin gauge theory. And from this spin gauge theory, when you gauge Z2 subgroup of the center one-form symmetry, you actually get SO2NC gauge theory. So let's see why that's the case. Okay, so for generic gauge G gauge theory with center C, you can consider gauging gamma subgroup of the center one-form symmetry, and this reduces the center to C over gamma. And correspondingly, the gauge group itself is also reduced to G over gamma. So if we take G to be spin 2NC and gamma to be Z2, then indeed we get G over gamma equals SO2NC. And one important fact is that there's actually a certain degree 2 Z2 valued cohomology class, which characterize the SO gauge bundles. And spin gauge bundles are the subclass, special subclass of SO gauge bundles with trivial W2. Sorry, the degree to cohomology class I call W2. And therefore, one can regard this W2 as a background gauge field for the Z2 one-form symmetry to be gauged from spin gauge theory point of view. So if you start from spin gauge theory and couple it to non-trivial W2, and then sum them over, if you gauge Z2 one-form symmetry, then you are actually summing over all possible SO gauge bundles, and that's by definition SO gauge theory. So that's how spin gauge theories and SO gauge theories are related. So they are related by gauging of Z2 one-form symmetry. But there's yet another subtlety. You have to be careful. So there's, by examining the possible line operator spectrum, Aharoni, Seiberg, and Tachikawa found that there's actually another SO gauge theory. So this theory differs from the ordinary SO gauge theory by what is called discrete theta angle. So recall that for SU gauge theory, we had a choice to incorporate theta angle, equivalently F wedge F term here, which captures the non-triviality, or namely instanton number of the gauge bundle. And for SO gauge theory, we have discrete analog of this, and thus the name discrete theta angle. But opposed to the ordinary theta angle case, theory with discrete theta angle and theory without discrete theta angle is not connected to each other. And two theories are actually distinct. So theory with discrete theta angle and theory without discrete theta angle is distinct. And we call the SO gauge theory with discrete theta angle an SO minus theory, while we call the ordinary SO gauge theory without discrete theta term an SO plus gauge theory. So there's this distinction between two SO gauge theories. And one technical remark for experts in the audience is that here we assume the space-time manifold to be equipped with spin structure for simplicity. One partial reason is that we will later incorporate fermions in the theory. So that's why we are assuming spin structure. But anyways, and this assuming spin structure, the discrete theta term is Z2 valued. So if you add the discrete theta term twice, then it has no effect. It becomes trivial. So that's the comment. So, okay, so to summarize, so if you start from spin to NC gauge theory, and if you just gauge Z2 one-form symmetry, and then you go to SO plus to NC gauge theory, while if you first add discrete theta term and then gauge Z2 one-form symmetry, you go to SO minus to NC gauge theory. Okay, so we saw that there are two operations appearing. So one is the gauging of Z2 one-form symmetry, and the other is addition of discrete theta term. And the surprising fact is that by carefully examining their action or effect, it turns out that these two transformations form an SL2Z2 group. And correspondingly, spin gauge theories, or SO plus and SO minus gauge theories, form an orbit under this SL2Z2 group action. So indeed, gauging Z2 one-form symmetry twice gives you back the original theory. And as I explained, since we assume spin structure on the space-time manifold, adding discrete theta term twice is equivalent to doing nothing. And finally, it turns out that acting T and S thrice brings you back to the original theory you started with.
Sorry, what group is this? Is it a permutation group of 3 elements, or is this?
Sorry?
What group is this?
It's SL2Z2.
Yes, but is it does it coincide with the permutation group of 3 elements, or is different?
So okay, so I think you should. So the situation is pictorially this. So let me repeat what I said. So if you start from spin gauge to NC gauge theory, and you gauge Z2 one-form symmetry, meaning that if you do the S transformation, you go to SO plus 2NC gauge theory. While if you first add discrete theta term and then gauge Z2 one-form symmetry, meaning that if you do T transformation and then S transformation, you go to SO minus 2NC gauge theory. So it's a transformation between different theories. Does that answer your question, or? Yeah.
So he was asking whether this aspect correspond to one permutation, one of the smallest group permutation, or something like this.
Permutation.
No, S2, S3, S4, 5.
Ah, yes, yes. Maybe. Okay, so anyway, we have this orbit under SL2Z2. And yes, so we are now finally coming to our main target. So let's add even number of massless fermions and vector representation to the spin gauge theories. So these additional fermions screen Wilson lines and vector representation away, and this reduces the center to Z2 for both NC even and NC odd case. So this means that the remaining Wilson lines are those in spinor representation. And if you don't care about the flavor symmetry at all, fusing two spinor Wilson line gives you either trivial Wilson line or vector Wilson line, depending on the parity of NC, where the latter is screened by dynamical quarks. However, the tricky point here is that fermions are actually charged not only under the gauge group, but also under the flavor group. And since -1 in the gauge group and -1 in the flavor group acts identically to the fermions, the screened vector Wilson line is not completely trivial, but actually carries non-trivial flavor charge. And this means that for NC odd case, Z2 one-form symmetry and flavor SU to NF zero-form symmetry are actually mixed. And it turns out that they actually form a two group. So this is found by Shin and Lam last year. So let me repeat. So spin QCD, spin 2NC QCD with 2NF flavors have two group symmetry when NC is odd. Okay, so we learned this by examining the flavor charge of line operators. So let's try to do the same thing in SO QCD case. So this time we have magnetic Z2 one-form symmetry, and the corresponding line operators are Tufte lines. And again, if you don't care about flavor at all, two Tufte lines fused together can be screened away by dynamical monopole, as you know. However, again, it is well known that magnetic monopoles can actually acquire non-trivial flavor charge due to quantization of fermionic zero modes. So I won't go into the details, but after some deformation, one can reduce the analysis to that of Tufte-Polyakov monopoles. And at last, it turns out that the magnetic monopole in this SO2NC QCD indeed carries non-trivial flavor charge. And as a result, SO2NC QCD with 2NF flavors have two group symmetry when NF is odd. So this is a story for SO plus theory, actually. But the story for SO minus theory is almost identical. And it turns out that SO minus 2NC QCD with 2NF flavors also have two group symmetry when NC plus NF is odd. Okay, so the results are summarized as follows. So in vertical direction, we have, so for spin QCD, we have two-group symmetry when NC is odd, corresponding to the bottom two lines, and SO plus QCD has two-group symmetry when NF is odd, corresponding to the bottom line. And finally, SO minus the QCD has two-group symmetry when NC plus NF is odd, corresponding to the middle two lines. And in horizontal direction, you see that when NC and NF are both even, nothing happens. NC is even and NF is odd. SO plus theory and SO minus theory has two-group symmetry, while in spin theory, spin QCD, the zero-form symmetry and one-form symmetry remain separate in a direct product. But
I have a question.
yes, sure, go ahead.
So as you said before, in a two-group is characterized by the zero-form group, the one-form group, but there's
Yes.
also cohomology class.
Yes.
So in this case, this cohomology class can only take a unique value, or there are different possibilities?
Thank you. It can have two different kinds of cohomology class for two groups. Yes.
So either zero or a non-trivial value.
Oh, sorry. How should I say? You can have two different kinds of two group symmetry. Yes. Yes, so in spin theory for NC even and NF odd, the two symmetries remain direct product. But actually, there's something non-trivial also going on for spin to NC QCD in this case. So now recall what I said in the at the end of the first section. So there was a relation between theory with two-group symmetry and theory with mixed Tooth anomaly between zero-form and one-form symmetries. So they were related to each other by gauging of one-form symmetry, which corresponds to S transformation situation. And if you carefully examine the action of S transformation and T transformation, it turns out that theory with mixed Tooth anomaly between zero-form and one-form symmetry and theory with two-group symmetry also forms the orbit under this SL2Z2 action. So if you start from theory with mixed Tooth anomaly between zero-form and one-form symmetries and gauge the one-form symmetry, you go to theory with two-group symmetry, while if you add discrete theta term, it does not affect the anomaly. While adding discrete theta term to one two-group symmetric theory, you get theory with two-group symmetry with different cohomology class, as you asked. So these two theories have different two-group structure. In a sense of different, having different cohomology class, yes. So as we have two SL2Z2 orbits, so one is the spin SO plus SO minus orbit, and the other is this mixed Tooth anomaly two-group orbits. So you can consider stacking them. And you can see which theories have which higher symmetry structures. Yes, sure, go ahead.
In the S transformation down there,
Down here.
yes.
Yes.
Why doesn't it go to an anomaly? I would expect that the two-group prime goes to an anomaly.
Yes, that's a good question. And yes, naively, we expect gauging two-group symmetry goes to theory of mixed Tooth anomaly. But because of this additional discrete theta term, the gauging procedure is somehow affected by this discrete theta term. And so if you have additional discrete theta term, then gauging gives you another theory with another kind of two-group symmetry in this case.
But here it's the same two-group symmetry as it seems to me. It's both the prime one, right?
You mean, are you asking that gauging before and after is
Yeah.
the same, you mean?
Yes.
So I'm not sure about the, deep insight about this, but it turns out that this is the case. Yeah.
Okay, thanks.
More practically, so if you can see that starting from ordinary two-group symmetric theory, acting T and S and T, you come back to the original theory. So that's what you know. And then the possible, only possibility is that there's these two group symmetric theories. Yes. Since we only have two kinds of two group symmetry here.
Thanks.
Okay, so the stacked results are the following. So the only possible assignments are the following. So for NC even and NF odd case, so recall that we had two group symmetry only for SO plus theories and SO minus theories. So the only possibility is that only possibility is that the spin QCD should have mixed Tooth anomaly between zero form flavor symmetry and one form center symmetry. Center, I'm not sure, but yeah, one form symmetry, zero form symmetry and one form symmetry, yes. And similarly for when NC is odd and NF is even, SO plus theory mixed Tooth anomaly. And finally for NC, when NC and NF are both odd, SO minus theory turns out to have mixed Tooth anomaly between zero form and one form symmetries. Okay, so now we've identified the higher symmetry structures in spin and SO plus and minus gauge theories. So let's now check how these higher symmetries are mapped under the Intriligator-Seiberg duality. So note that making theory supersymmetric does not affect the relevant symmetry and thus does not affect the argument. So supersymmetric QCD also had the same two group symmetry, higher symmetry structures with non-supersymmetric ones. So the Intriligator-Seiberg duality is a duality which exchange the supersymmetric QCD with SO-NC gauge algebra with NF flavors with supersymmetric gauge theory with SO-NF minus NC plus 4 gauge algebra with the same number of flavors. So as you know, there's various tests of this. So you can, for example, match zero form symmetries and their anomalies, or you can also match gauge invariant operators and so on. But you can be more precise about the global form of the gauge group. And it turns out that the results are following. So actually, the spin QCD, SQCD, is mapped to SO minus SQCD on the dual side. And SO plus SQCD is mapped to SO plus SQCD on the dual side. And finally, SO minus theory is mapped to spin theory on the dual side with additional discrete theta term. And there's also a test of this. So by matching superconformal indices on lens spaces, I think. But yes, anyway, so this is the mapping under the Intriligator-Seiberg duality. Oh, so T is the T transformation of the SL2Z2 group, which is the addition of discrete theta term. Addition of discrete theta term. Yes. So again, pictorially, we have this kind of orbit. So the Intriligator-Seiberg duality maps this spin theory to SO minus theory with discrete theta term, SO plus theory to SO plus theory with discrete theta term, and finally SO minus theory to spin theory with discrete theta term. So actually, if you flip the orbit on the left-hand side upside down, you get the orbit in the right-hand side. So that's the action of the Intriligator-Seiberg duality. And then it's now straightforward to check how higher symmetry structures are mapped under the duality. So for example, for NC even and NF odd, the dual theory has NC odd and NF odd. So you can substitute the result we saw in the previous section. So, and then it turns out that the higher symmetry structures are indeed matched perfectly across Intriligator-Seiberg duality. So similarly for NC odd and NF even case, the dual theory also has NC odd and NF even. And again, you can see that higher symmetry structures are mapped appropriately under the duality. Okay, so that's,
May I?
yes, sure, go
question?
ahead.
So if you take this a special value of the NF,
Yes.
which is 2nc minus 4 or minus 2, the theory
Yes.
should be self-dual.
For special value of NC and NF, yes.
At least at the level of the algebra. So the duality should be a transformation, same set of theories.
Yes, so that's, I mean, so I think this should be the case. So that special case should be the subclass of this, right? Since it should have the same parity before and after the duality, right?
Yes, since it is the same number.
Yes, yes, yes.
So, I mean, is there something more to say in that case? Because now you have one more internal. I mean,
it's more than
either this duality becomes an extra symmetry of the theory, or it must within the same this diagram. I don't know.
Extra symmetry when, I mean, for the special value of NC and NF, you mean? Oh, sorry, that's not what you're saying.
Yeah, I mean, for this special value, let's see. So for the special value, the algebra is the same. I'm not sure that the theory is the same because maybe the global form of the group is not the same.
Yes, global form itself is different. I mean, there's no pair of the same global structure, so yes.
Yeah, I was just wondering if there is some extra
self-dual something.
I don't know, argument or something extra to say in that case or not.
I see. Oh, yeah. I mean,
yes, it's not the same theory. Yes. Okay.
Yeah, so maybe you can ask me later then. Yeah.
Okay. Yes.
Okay, so that's basically the main content of this talk. So, but some of you might have noticed that the way of indicating the existence of mixed Tooth anomaly in QCDs was somewhat indirect. And you might ask, why don't you just directly compute this mixed Tooth anomaly 0.1 from symmetry? So in the remaining time, I will describe the Bordism and invertible QFT and explain how these are related to anomalies and see that the direct computation of mixed Tooth anomaly is actually very difficult, unfortunately. Okay, so let's start from Bordism. So what is the Bordism? So Bordism group, Bordism is a group, which is an abelian group formed by certain equivalence classes of closed manifolds. So here two closed D manifolds, MD and MD prime, are defined to be equivalent if there exists a one higher dimensional manifold, WD plus one, which connects them. And such MD and MD prime are said to be bordant to each other. And the group operation, binary operation we want to consider is a disjoint union of manifolds. So if you have two manifolds, say A and B, the disjoint union of A and B is just this, which is also closed. And also the disjoint union between A and the empty D manifold is A itself. And therefore, these closed D manifolds themselves form a monoid under disjoint union, where the identity element is this empty D manifold. On the other hand, the equivalence classes we defined forms an abelian group under disjoint union, where the identity equivalence class consists of those bordant to an empty D manifold. Or equivalently, in other words, closed D manifolds which can bound a one higher dimensional manifold. So that's the identity equivalence class. And the group structure arises since for any closed D manifolds, there always exists its inverse equivalence class, to which the orientation reversal belongs. So let me further elaborate on that. So for two Bordant manifolds, A and B, one can stretch the bulk. And as a result, you can see that the disjoint union of A and the orientation reversal of B is Bordant to an empty D manifold. And since any closed D manifold is Bordant to itself, so A, so disjoint union of A and the orientation reversal of A is also Bordant to an empty D manifold. And as a result, a orientation reversal of A belongs to the inverse equivalence class of the original equivalence class. So that's how the group structure emerges. And that's the basic definition of the Bordism group, but one can easily extend this notion and take various structures of manifolds into account. So for example, if you take MD and MD prime to be spin closed D manifolds, and require the spin structure to be suitably extended across this WD plus 1, then the resulting group becomes spin Bordism group. So due to the lack of time, I will skip these examples, but you can. Okay, then I'll go with the example. Okay, so let's work out some example then. So let's start from oriented Bordism case. So for 0 dimensions, the oriented Bordism group is generated by a point. And as is shown, the point is Bordant to itself. And also its inverse is a point with opposite orientation. And the oriented Bordism group in 0 dimension is actually Z, which corresponds to the net number of points with same orientation. So next, let's look at the one-dimensional case. So for one-dimensional case, so candidate generator manifold would be S1, a circle. But as you know, the two-dimensional disk is bounded by a one-dimensional circle. So it is actually Bordant to an empty one manifold. Or you can also see this from a pair of pants. So you have two circles on one side and one circle on the other side. So if you drop one circle from each side, then again, you'll see that the circle is Bordant to an empty one manifold. And as a result, one-dimensional oriented Bordism group is trivial. And you can go up to higher dimensions in a similar manner, and you'll find a 2D and 3D oriented Bordism group is trivial, while 4D oriented Bordism group is not trivial and generated by CP2. But if you further take spin structures into account, some of the Bordism groups get modified. So for one-dimensional case, so by taking spin structures into account, there's actually two types of circle. So one is a circle with periodic boundary condition, and the other is a circle with anti-periodic boundary condition. And it is known that the two-dimensional disk with spin structure is actually bounded by anti-periodic circle. And as a result, this anti-periodic circle is Bordant to an empty one manifold, while periodic circle is not Bordant to an empty one manifold. And as a result, this periodic circle becomes the generator of one-dimensional Bordism group. And so it is also known that in a form of pair of pants, the two periodic circles can be connected to a single anti-periodic circle, which is Bordant to an empty one manifold. So as a result, the one-dimensional spin Bordism group turns out to be Z2. Okay, so as you have seen, so there are many different kinds of Bordism group, depending on what kind of structures of manifold you want to consider. And for our purpose, the structure we want to consider is a spin structure plus this map from manifold to another space X, which is to be identified with the target space of the QFT. And this defines the relevant Bordism group here, so omega d spin of X. So this Bordism group is what we want to consider later. Okay, so that's it for the Bordism. And let's move on to the invertible QFT then. So what is invertible QFT? So it is simply defined to be a QFT having one-dimensional Hilbert space on any closed spatial slice. So one might think that such QFT is trivial, but that's actually not the case. There can be non-trivial QFT with non-trivial partition function, even though the Hilbert space is one-dimensional. And these theories are invertible in the following sense. So given two QFTs, Q and Q prime, one can produce a new QFT by stacking them, meaning that taking product of partition functions and taking tensor product of Hilbert spaces. And generic QFTs form a monoid under this operation, where the identity element is a trivial QFT with trivial partition function and trivial Hilbert space. But for QFTs with one-dimensional Hilbert space, there always exists its inverse. So it is just a QFT with inverse partition function and a dual Hilbert space, which is also one-dimensional. So if you start from original QFT with one-dimensional Hilbert space, and then couple it to dual invertible QFT, dual QFT with one-dimensional Hilbert space, you indeed get trivial QFT, and they form a group. So that's why they are called invertible. And the recent understanding is that these invertible QFTs can actually be classified up to continuous deformation by this group sitting in the middle of this short exact sequence. So here, up to continuous deformation means we identify any two QFTs which can be connected, which can be deformed to each other by changing the values of continuously tunable parameters. Okay, so invertible QFTs themselves already form a group, as we saw in the previous slide. But by looking at certain nice equivalence class, it reduces to a nicer group, which we relatively have grasp of this kind of description. So as you can see, this group essentially consists of two pods. So one is this torsion pod of d-dimensional Bordism group, and the other is this free pod of the d+1 dimensional Bordism group. So if you want to know how, what kind of invertible QFTs there are, you can just compute these two Bordism groups and determine them. And the computation is, of course, not easy in general, but thanks to mathematicians, there are many powerful computational tools. For example, Atiyah-Hertzberg spectral sequence or Adams spectral sequence, which enable us to extract partial information on Bordism groups, and sometimes even allow us to fully determine the desired Bordism group. So I won't explain the details of these spectral sequences, but you can think of them as some kind of black boxes which tell you the Bordism group of your favorite space X by throwing in the homology or cohomology information of that space X as an input. So yes, so that was the story about invertible QFT and Bordism. And so how are they related to anomalies then? So the point is that we believe that any d-dimensional anomalous QFT is realized as a boundary of one higher dimensional invertible QFT, which sounds quite reasonable from various knowledge about anomaly inflow examples. So that's the belief. And based on this belief, one can classify possible anomalies in terms of Bordism group, since the invertible QFTs were classified by Bordism groups. So that's how they should be related. So let's, again, look at some examples. So let's consider the 3+1 dimensional SUN gauge theory. So 4-dimensional anomalous QFT was realized as we believe that it is realized as a boundary of a 5-dimensional invertible QFT. So we should look at this group, which consists of these two Bordism groups, where X is what is called, BSUN, what is called classifying space of the gauge group SUN, but you don't have to precise about that anyway. So you can, in this case, you can compute these Bordism groups completely, and the results are the following. So it turns out these are the results. And it indeed captures the information on anomaly. So for n larger than or equal to 3, sorry, the SUN gauge theory might suffer from perturbative gauge anomaly for n larger than or equal to 3, while it does not for n equals 2. Meanwhile, for n equals 2, theory might suffer from Whitman's global gauge anomaly, while, I mean, in contrast, there's no such global anomaly for n larger than or equal to 3 case. So indeed, this Bordism thing somehow captures the anomaly information. So after this lengthy preparation, we are now coming back to the original problem. So the relevant Bordism group, which should capture this anomaly coming from fermions, should be this, which is quite complicated, as you can see. And again, so in principle, if you compute this Bordism group, and it's done, but unfortunately, this computation is very, very hard. And so we did as much as possible, and we gave some checks, including the easiest case. So for easiest case, which is namely the NC equals 2 and NF equals 1 case, we managed to do the computation, and it indeed reproduced the desired form of mixed anomaly at last. Yes, do you have a question?
Yes. So here you are putting on the same footing the gauge and the say, flavor anomaly.
Yes.
And
so
at some point, I guess you want to disentangle them, no? Because okay, gauge anomaly should be 0, but the flavor anomaly is what you want to compute.
The gauging operation itself does not affect the form of anomaly, right?
I mean, SO2 and C is the gauge group.
Yes. Okay. So yeah,
So I mean, here you are classifying in the same box the gauge anomaly and the flavor anomaly.
Yes.
Or global anomaly, call it as you want.
Sorry, I didn't quite get your question. So, but I mean, so you have SO gauge theory with SU flavor symmetry, right? You can ungauge SO gauge group, right? I mean, the gauging procedure does not affect the form of anomaly itself, right?
Yes, I'm just saying that usually when you talk about a quantum field theory, interacting, I mean, you as a black box, there is a global symmetry, and usually you talk about the Toft anomaly for the global symmetry. But here you are putting together, you know, the gauge symmetry, so the gauge anomaly and the flavor anomaly.
I mean, since how should I say? I mean, since this is the full group under which fermions are charged, right? And in that sense, I mean, this full group is the appropriate group to consider. I mean, this group is, I mean, sorry, a Bordism group of classifying space of this group is the Bordism group which captures the anomaly coming from fermions in this case. Is that
okay?
There's that. Okay. This also classifies mixed gauge flavor anomalies.
Yeah, sure.
So what he's saying is that as soon as you find what is the anomaly, you will have to find a way to cancel it if you want to integrate over the SO and C part. If you want to gauge the SO2 and C part, once you know what is the anomaly, you will have to find a way to cancel it. And so in the end, I mean, it's good to find the anomaly, but then you will have to remove it somewhere.
I mean,
Yes, because I mean, these classified, say, type of anomalies, but at the end of the day, we know the gauge anomaly will be 0. Otherwise, the filter does not make sense.
Yes.
As Diego was saying, there are the mixed gauge flavor anomalies. They can either potentially remove part of the global symmetry, they can give rise to two-group structure, and then there will be a part which is the Toft anomaly of the true global symmetry of the theory. So now here in a box, you're putting all these different type of anomalies that will have at the end very different interpretation.
Okay, then let me change the, I mean, okay, so if you compute that Bordism group, then there might be such, I mean, various type of anomalies, but okay, at least for this case, I mean, the easiest case, it turns out that this group is Z2, and meaning that there's only one type of anomaly, and it turns out that the form is this type of form, which is the mixed Tuft anomaly between zero form, which explains the zero forms mixed Tuft anomaly between zero form and one form symmetries. So, I mean, by looking at this, you can see that there's no other type of anomaly. So,
okay.
Yeah. Yes.
So does this mean this latter example that I'm not allowed to gauge SU2 symmetry because this way it's my true gauge will not be well defined, integration of gauge fields. If I have this mixed anomaly, it just means that I'm not allowed to gauge SU2, right?
Yes, yeah. I mean, okay.
If I put background for SU2 part, then SO4
yes,
variant, and I cannot integrate with analytical gauge.
Yes, indeed, yes. I mean, yeah. I mean, actually, the full SU2NF, I mean, this A2 part is not capturing the full SU2NF part, but only the centered Z2 part. So that's the bit subtle point, but yes, essentially, you're right, yes.
How does the knowledge of the Bordism group imply and give us then the precise invertible phase that we have to put?
So this is, okay, how should I say? This is kind of art, you can say. I mean, to explain how to get this concrete form, I think you have to go into the details of the calculation of spectral sequences, but I mean, in a way, it turns out that the form should be this type, and yes, that's the
Perfect. Thanks.
Yeah, so spectral sequence computation can not only just compute the form of the group, but can also sometimes identify this element generating that group. Yes. Okay. Oh, so. Okay, great. Okay, so let me summarize my talk then. So we've looked into SO QCDs and spin QCDs with even number of colors and even number of flavors in 3+1 dimensions. And there was two group symmetry or mixed Tuft anomaly between 0 form and 1 form symmetries. And two group symmetry was detected by looking at line operators and finding non-trivial flavor charge of them. And mixed Tuft anomaly was able to detect by either looking at the SL2Z2 orbit and stacking them, or from Bordism group, which is a bit incomplete, but there's various checks. And in particular, for n equals 1 supersymmetric QCD case, we saw that higher symmetry structures are mapped appropriately under Intriligator-Seiberg duality. So that's all I wanted to say. So thank you very much for your attention.
Okay, thank you. So do we have more questions?
Yes. I have
Go ahead, please.
very last. So you didn't explain how these two group symmetry acts, because if one act on point, the other act on lines,
Okay. Yes.
and it is not a trivial product.
Okay, sorry. Okay.
So where is the catch?
Okay, so actually
If I take the composite state of a line and a point,
yes.
I act as before, I get the trivial action. Trivial, I mean, not trivial action, trivial tensor product.
So
But you say it is not a trivial tensor
So actually, the
product.
relevant part of that zero form symmetry acting on point is that, sorry, I shouldn't say point, but so the relevant part of flavor symmetry is actually only the Z2, how should I say, Z2 one form center of that flavor SU2NF. So, in some sense, that zero form flavor symmetry is transformed into Z2 one form flavor, how should I say? Z2 one form symmetry where the flavor Wilson line is charged. So it both acts on lines. The full, yes, as you say, full SU2NF flavors acts on local operators, but the relevant part is only the Z2 center part, and that only acts on line operators. And yes, that's why, gauge center part and flavor center part both acts on line operators. So it doesn't, the two group symmetry thing is only, how should I say, the story on the line operator side. Does this answer your question or so? Maybe you can ask me later, yes.
Do we have more questions? Yes.
So in the, this anomaly that you just showed us,
Yes.
I didn't really understand. So it's an anomaly between the center symmetry and the flavor symmetry, or is it?
Yes. So this W2 is, this W2 is the background gauge field for Z2 one-form symmetry of the spin gauge theory, right? Yeah.
Right. So it's
right. And
between
this,
the one form center symmetry
and this A2 thing is the how should I say?
The background for the SU2?
Background gauge field for Z2, Z2 one form symmetry coming from flavor SU2NF group.
I see.
So it's the analog of W2 in the SU flavor side, actually.
So it's a mixed symmetry, a mixed anomaly between the two one form symmetries, or not?
Yes.
Okay.
I see. Yeah. So that's what that's Andrea also asked. So
okay, thanks.
Now that we are speaking about this mass, what is beta?
Okay. Beta is some kind of operation which takes cohomology class with degree 2 to cohomology class with degree 3. So if you want to name, it's called something called the Bochstein operator.
The Bochstein.
Yes.
Oh. Okay, thank you.
Other questions? Okay, if not, let's thank Yasunori.
So let's also thank the organizers for organizing this kind of wonderful workshop. So thank you, Andrea, and thank you, Francesco, especially. Was there someone saying something and not? Maybe not. Okay. Yeah.
Okay, so I want to finish. I also want to say a couple of things. So first of all, we want to thank the GGI staff and all the organization NFN that made this possible. And thank you for participating in spite of all the difficulties of this time. I hope this is a starting for a better, more normal activity. And let me thank the organizers, so myself as well. Okay, and that's it. Okay.